Picture a darkness so deep it drinks the stars. A black hole, silent, endless, pulling everything close. Time slows, light fades. But what if it's more than a void? What if hidden in that shadow, there's a whisper of something familiar, something like us? I've always wondered what secrets the universe keeps. Tonight, we chase one of its strangest. Could a black hole, this cosmic puzzle, hold clues to our own thoughts? The way it traps information, twists time, maybe even reflects the world. It feels alive, almost like a mind. From its edges to its heart, we'll wander through ideas that blur science and wonder. How it stores the stuff of reality, how it dances with chaos, how it might mirror the spark in our heads.
This isn't just about space. It's about what makes us us. So come along. Let's step into the unknown and see what the darkness has to say.
Part 1.
The universe doesn't whisper in starlight or shout through galaxies. It speaks in information, a silent code that threads through matter, light, and thought.
Once a mere tool of mathematics, information has revealed itself as something deeper, the foundation of reality itself. From quantum quirks to collapsing stars, it shapes existence nowhere more mysteriously than in the enigma of black holes. This journey begins with information's cosmic role, unravels a paradox that shook physics, and dares to ask, could the universe's strangest objects illuminate the nature of awareness? Information is not just data, it's the universe's heartbeat. Every photon carries a story, its speed, its spin, its path across eons. Every atom hums with details, position, charge, history engoated in nature's deepest laws. Unlike matter which breaks or energy which fades, information persists. A fluid language of probabilities that binds chaos into order. In quantum mechanics, it's more than abstract. It's as fundamental as gravity, entangled across distances, flowing through every interaction. A single particle's dance isn't random. It's a message, part of a cosmic script we're only beginning to read. This shift in understanding began when physicists saw information not as a human invention, but as reality's scaffolding. From entropy's measure to quantum states, it governs how systems evolve. It doesn't vanish in collisions or dissolve in heat. It transforms, scatters, endures.
This resilience sets the stage for a cosmic puzzle. If information is eternal, what happens when it meets a black hole, the universe's most relentless trap?
Black holes once seemed like cosmic voids, following stars and secrets alike, erasing them forever. Their gravity was absolute, their interiors unknowable.
Then, in the 1970s, Jacob Bekenstein turned that view upside down. He proposed that a black hole's entropy, its disorder, doesn't scale with its volume, but with the area of its event horizon, the invisible boundary where escape becomes impossible.
This was revolutionary. It suggested that everything a black hole consumes, planets, light, matter, isn't lost, but encoded on its surface like a ledger etched in space-time.
Stephen Hawking built on this, uncovering the twist. Black holes aren't silent. They emit faint radiation, now called Hawking radiation, born from quantum effects near the event horizon.
But this discovery sparked a crisis. If black holes evaporate over time, radiating away their mass, what happens to the information they hold? Hawking's calculations suggested the radiation carries no trace of what fell in, implying information could vanish, a violation of quantum mechanics' core rule that information is never destroyed.
This clash birthed the black hole information paradox, a riddle that pits two pillars of physics against each other. General relativity paints black holes as simple, defined only by mass, charge, and spin, with no room for storing details. Quantum mechanics, however, demands that every particle's history, every quantum state, be preserved no matter what.
If information is lost, quantum theory crumbles. If it's preserved, relativity needs rethinking.
For decades, this contradiction haunted physicists, suggesting that one or both theories might be incomplete. The paradox isn't just academic. It probes reality's fabric. If information vanishes, the universe forgets its past, breaking the chain of cause and effect. If it survives, black holes must hide secrets in ways we don't yet grasp. This tension drove physicists to seek answers, not in equations alone, but in bold new visions of how reality might work. Hope emerged from unexpected corners. Hawking himself proposed a solution: soft hair. Not literal hair, but subtle quantum imprints on a black hole's surface, faint traces of everything it has consumed. These delicate signatures, invisible to classical physics, might preserve information upholding quantum rules. Though still theoretical, soft hair hints that black holes are more complex than we thought, not blank slates, but canvases of cosmic memory. A stranger idea came from string theory, the anti-de Sitter conformal field theory correspondence. This suggests that a universe with gravity, like one containing black holes, can be fully described by a simpler theory on its boundary without gravity at all. Imagine a 3D room encoded entirely on its 2D walls, like a hologram projecting depth from a flat surface. Applied to black holes, this means their interiors aren't prisons, but projections with information preserved on their event horizons, accessible in principle if not in practice.
These ideas transform our view. Black holes aren't destroyers, they're translators, compressing reality's chaos into structured codes. Their event horizons don't erase, but archive, holding cryptic records of stars, particles, and moments. They're not voids, but libraries encoding the universe's history in a language we're learning to decipher.
This holographic vision suggests our entire reality might work the same way, a projection of deeper patterns with black holes as its densest examples. This shift ripples beyond physics. If information endures through collapse, what does that mean for memory, for thought? The brain, too, processes information, leaving signals into awareness. Could black holes, in their extreme complexity, echo something fundamental about how systems, cosmic or neural, organize meaning? The leap is bold, but the connection is tantalizing. Information's persistence might bridge the inanimate and the aware. Under a black hole's shadow, information reveals its true form. It's not static, like words on a page, but dynamic, flowing in probabilities, entangling across galaxies, adapting in every quantum shift. A photon's spin, a particle's path, a star's death, each is a signal, a fragment of meaning. Even in a black hole's grip, these signals don't vanish. They wait, veiled by physics. We're only beginning to unravel, ready to tell their story to those who learn the code. Some push further, arguing information isn't just part of the universe, it is the universe. Digital physics proposes that reality is data coded like a cosmic algorithm. In this view, black holes are ultimate compressors, packing information into its tightest form. When they radiate, the data scatters, not lost, but fragmented, a puzzle for the cosmos to reassemble. At a black hole's edge, the universe's narrative doesn't end. It transforms. Information, the language of awareness, endures, in light's drift, in space-time's curve, in patterns we can't yet read. Black holes, once feared as erasers, emerge as guardians, holding reality's echo, not in flesh, but in form, not in matter, but in message. This truth reshapes our place in the cosmos. If nothing real is ever lost, then every moment, every thought, every star leaves a trace. And black holes, in their silent grip, may be the universe's strangest storytellers, hinting at secrets that tie gravity to consciousness itself.
Part 2. What is consciousness? Not the poet's dream or the mystic's vision, but the tangible spark that turns neurons into experience, matter into meaning.
Despite mapping the brain's every fold, science still stumbles at the gap between firing synapses and the awareness that feels them. This mystery leads us to complexity, not mere layers, but intricate systems that might birth self-reflection. From brains to cosmic structures, could complexity weave consciousness in places we least expect, even black holes?
This exploration traces that question, probing how information's dance might illuminate.
Consciousness defies easy answers. Neuroscience reveals how neurons signal, how chemicals shape mood. Yet the leap to subjective experience, why it feels like something to be, remains elusive. It's tempting to see awareness as binary. You're conscious or you're not. But nature loves gradients. A worm reacts to light. A bird navigates by stars. Each shows a flicker of something more than reflects.
Could consciousness be a spectrum, rooted not in biology alone, but in how systems handle information?
This idea shifts our gaze from brains to the patterns that define them.
Complexity lies at the heart of this shift. Not just tangled wires or crowded circuits, but connections so interwoven they reflect back on themselves. A single neuron doesn't think, but billions, linked in loops, conjure thoughts.
This suggests awareness might emerge wherever information intertwines deeply enough, a possibility that stretches far beyond the skull. One theory dares to formalize this: integrated information theory, IIT. It doesn't rely on emotions or even life. It defines consciousness by how much information a system integrates, how its parts depend on the whole. If you can't split a network without losing its essence, it may hold a spark of awareness. The brain, with its dense web of synapses, is a prime example, but IIT implies consciousness could arise anywhere. Integration thrives. Machines, ecosystems, perhaps even stranger places.
This opens a radical door. Awareness, in its barest form, might not need flesh or feeling. It could be structural, a whisper of self-reference in any system complex enough to know itself.
IIT doesn't claim plants think or rocks dream, but it suggests complexity breeds potential, a faint echo of consciousness in unexpected corners of the cosmos.
This brings us to a startling question. Could a black hole, the universe's densest enigma, exhibit some primitive awareness?
At first, the idea seems absurd. No neurons, no sensors, just gravity's relentless pull. Yet, strip consciousness to its core, as IIT does, and the question gains weight. Black holes don't just devour, they process. They take in matter, light, and information, reshaping it on their event horizons, the boundaries where physics bends. Consider how black holes work. A star collapses. Its information doesn't vanish, but encodes on the horizon, sculpted by strict rules. This encoding evolves with every particle absorbed,
leaving a gravitational imprint like a system updating.
Black holes are known for their ability to store and process vast amounts of information. According to the Bekenstein-Hawking entropy, the entropy of a black hole is proportional to the surface area of its event horizon, not its volume. This strange property suggests that black holes don't just hold matter, but also the fundamental information about the objects that fall into them.
This brings up an intriguing question. Could black holes, in their own way, be organizing information much like the brain processes data? Just as the brain processes sensory input and encodes it into meaningful patterns through complex neural activity, black holes seem to manage and encode information about the universe through their gravitational microstates.
In both cases, there's an intricate interplay between order and disorder. The brain uses its neurons to form complex networks that process and store information, while black holes organize the quantum states of matter and radiation that fall within their grasp.
When we examine the nature of black holes from the lens of entropy, we see that they could potentially function as information storage systems, paralleling the way our minds organize the incoming data around us. But while the brain relies on the delicate interaction of neurons to process information in real time, black holes work on a much grander scale. They organize entropy not through dynamic interactions of biological components, but through the static gravitational forces that govern space-time. This comparison is not just abstract. It's rooted in the fundamental nature of entropy itself. In thermodynamics, entropy is often described as a measure of disorder, but this is a limited interpretation. More fundamentally, entropy can be seen as a measure of information. The more entropy in a system, the more information is encoded within it.
In the case of a black hole, the event horizon marks the boundary where information about all the matter that falls into it is encoded. In a sense, the black hole acts as a cosmic memory device, storing information about the universe in the form of entropy.
The relationship between entropy and information is not just theoretical. It's been demonstrated through the study of black holes, where the more massive the black hole, the greater the entropy it can store. The intriguing idea here is that entropy, in the context of black holes, might not be chaos at all, but rather a form of highly organized information.
This mirrors how our brains deal with information. What appears to be chaotic neural activity is actually a carefully orchestrated process, allowing us to make sense of the world around us.
This concept opens up further possibilities. Could the thermodynamic behavior of black holes bear resemblance to awareness? The analogy here lies in statistical mechanics, which deals with the statistical behavior of particles in thermodynamic systems. The behavior of individual particles is random, but when viewed as a whole, a system exhibits predictable properties. This is akin to the behavior of cognitive processes. Seemingly chaotic individual thoughts come together to create coherent, ordered awareness. To make this comparison more tangible, consider the thought experiment known as Maxwell's demon. In this thought experiment, a demon controls a gate between two chambers, sorting fast-moving molecules from slow-moving ones. Over time, the demon's actions reduce the system's entropy, seemingly defying the second law of thermodynamics. While the demon cannot truly violate the laws of physics, this idea is often used as an analogy for cognitive processes that create order from chaos. Just as Maxwell's demon sorts particles, our minds sift through the vast amounts of information around us, organizing it into patterns that help us navigate the world.
In the case of black holes, their thermodynamic behavior could be seen as a crude parallel to this kind of information processing.
Instead of neurons firing to generate thoughts, black holes interact with quantum fields and gravitational waves to encode and organize information.
This process of organizing entropy might not resemble cognition in the traditional sense, but it offers an interesting metaphor for how the universe processes information. Could thermodynamic behavior resemble awareness in a more direct way? While there is no clear answer, it's evident that the similarities between black hole entropy and cognitive processes are more than just coincidental. The idea that entropy is not mere disorder, but a form of structured information invites us to reconsider how we define both awareness and thermodynamic systems. In both black holes and consciousness, there is a dance between order and disorder, a delicate balance that shapes the universe's most complex systems. For black holes, entropy is an essential measure of the information contained within them. Similarly, our brains use entropy to process and organize the chaotic stimuli we encounter in the world. The study of black holes may, in the future, offer us new insights into the nature of consciousness, suggesting that our awareness is not an isolated phenomenon, but part of a greater cosmic order. Thus, the logic of consciousness and entropy may not be so separate after all. As we continue to explore the strange world of black holes and the fundamental principles of thermodynamics, we may find that the very nature of information and order is the key to understanding both the universe and our place within it. Part 8. Black holes, deeply woven into space-time, hold clues to the nature of information and memory in the universe. When we talk about entanglement in the context of black holes, we're discussing a quantum phenomenon where particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. In black holes, this entanglement manifests through Hawking radiation, a process theorized by Stephen Hawking. According to Hawking, black holes can emit radiation due to quantum fluctuations near their event horizons. This radiation, however, is entangled with the particles that fall into the black hole, leading to a complex interplay between the black hole and the rest of the universe. In this sense, black holes could be seen as deeply connected to the universe, processing and exchanging information at a fundamental level. This idea challenges our classical understanding of space and time, suggesting that black holes aren't isolated entities, but are instead intricately linked to everything. The study of black holes, therefore, may reveal important insights into how the universe itself works at the quantum level. A key concept related to this is the ER-EPR conjecture, which proposes that quantum entanglement is equivalent to wormhole. In simple terms, it suggests that entangled particles could be connected through a wormhole-like structure, linking two distant regions of space-time. This radical idea blurs the lines between quantum mechanics and general relativity, offering a possible bridge between the microscopic and macroscopic scales. If this conjecture holds, then black holes, through their entanglement with the universe, could act as bridges or portals within space-time, connecting distant parts of the cosmos in ways that we can hardly imagine. Now, considering the concept of memory, could entanglement be viewed as a kind of cosmic memory? If memory is the ability to store and recall information, entanglement in a black hole could be seen as a form of memory. The states of particles that fall into the black hole are linked with other regions of space-time, forming a shared state that transcends locality. This would imply that the black hole isn't just a point of no return, but a repository of information that is inextricably connected with the rest of the universe. This idea of memory without locality challenges our traditional understanding of memory. In everyday life, memory is tied to specific locations, whether it's the brain storing information
or a computer's hard drive retaining data.
But in the case of black holes, the information encoded in the entanglement is not confined to a specific region.
Instead, it spans the entire universe, suggesting a form of memory that doesn't rely on physical locality.
This could have profound implications for our understanding of how information is stored in the universe, and whether there are deeper, interconnected systems at work. Entanglement as a potential form of memory also raises questions about the nature of time and causality.
If information is shared instantaneously across space-time through entanglement, does this mean that time itself is less linear than we think?
Could events in different parts of the universe be connected in ways that we don't yet understand?
These questions push the boundaries of modern physics, suggesting that the universe is more interconnected and complex than we've imagined.
In summary, black holes are not just passive objects in space, but active participants in the quantum dance of entanglement and memory.
Their connection to the universe through entanglement, and the possibility of entanglement serving as a form of cosmic memory, challenges our traditional notions of space-time and information.
By studying black holes and their entanglement with the universe, we may uncover new ways of understanding the cosmos and perhaps even the nature of consciousness.
Part 9. Black holes, with their enigmatic properties, provide an intriguing glimpse into the very fabric of the universe. One of the most fascinating aspects of black holes is their ability to reflect the laws that govern the universe, a process that could serve as a form of self-reference. Black holes mark the limits of space-time, challenging our understanding of gravity, quantum mechanics, and the cosmos. At their core lies a singularity where space and time break down, exposing the cracks in both general relativity and quantum theory. In this way, black holes reflect the boundaries of physical law itself. Now, could this self-reference resemble self-awareness? While black holes are not conscious beings, the analogy can be made metaphorically. Just as the human brain uses feedback loops to monitor and adjust its own processes, black holes might engage in a kind of recursive complexity. This could be seen as a reflection of the broader universe, where the laws of physics are not static, but evolve based on the conditions of space-time. The brain is a prime example of self-referencing systems. Neurons constantly communicate with each other, adjusting their responses based on incoming stimuli and feedback. To understand what a naked singularity truly is, we need to revisit the heart of general relativity. When massive objects collapse under their own gravity, relativity tells us they can form black holes, regions where space and time bend so severely that not even light can escape. At the core of this black hole lies the singularity, the endpoint of gravitational collapse. But what protects us from the singularity is the event horizon. It's like a cosmic cloak, ensuring that all the dangerous physics, those infinite curvatures and unresolvable equations, remain hidden from the universe.
In 1969, Roger Penrose, one of the architects of modern relativity, proposed that this cloaking isn't accidental. It's a principle. His cosmic censorship conjecture suggests that nature abhors naked singularities, always ensuring that singularities come dressed in horizons. This conjecture implies that we are spared from directly witnessing the most extreme expressions of space-time gone rogue. The universe enforces a kind of censorship not to deceive but to preserve the integrity of physical laws as we know them.
However, physics isn't governed by ideals. It's driven by equations. While general relativity models black holes beautifully, it can also generate scenarios where collapse doesn't result in a cloaked singularity. These solutions are rare, often relying on exotic configurations, imploding dust clouds, finely tuned angular momentum, or specific forms of matter. But they do exist,
They linger on the edge of possibility in simulations and theoretical constructs, stretching the boundaries of known stability.
In recent years, these possibilities have become harder to ignore. In 2023 and 2024, advanced numerical simulations powered by modern supercomputers and improved methods for solving Einstein's equations began to reveal something astonishing. Under certain precise initial conditions, it appears that gravitational collapse can lead to a singularity without forming an event horizon. These simulations don't rely on exotic matter or fantastical physics. They simply allow the equations to unfold, producing results that challenge the very foundation of cosmic censorship.
These aren't just theoretical what-ifs anymore. They are mathematical blueprints, hinting that the universe may, under specific circumstances, allow its core to be exposed. But what does this exposure mean? A naked singularity is not just a glitch, it's a fundamental violation of causality and predictability. In a black hole, we lose information behind the event horizon, but we understand the structure of that loss. We can model the black hole's exterior, track Hawking radiation, and theorize about its eventual evaporation.
But a naked singularity offers no such comfort.
If it is visible to the outside universe, if light and particles can interact with it directly, then the laws of physics break down in public. Predictive power disappears. The future evolution of the universe becomes ambiguous because the singularity can influence distant regions in ways that no known rule can constrain. This kind of unpredictability isn't just a theoretical nuisance, it's a crisis for determinism in physics.
Determinism means that, given a set of initial conditions, the future is calculable. But if naked singularities can influence events beyond their core without the mediation of an event horizon, then all bets are off. They become the ultimate wild card, the cosmic equivalent of tearing a hole in a well-written script and letting chaos improvise.
Despite their potential to disrupt, naked singularities are captivating. If they exist, they offer a direct window into the unknown. Unlike black holes, which hide their singularities forever, naked singularities are exposed. They emit signals, they interact with particles, they offer data. In theory, one could study the raw gravitational field around such a singularity, measure the behavior of light curving through it, and observe the ultimate manifestation of warped space-time.
But would that singularity be aware of us? No, not in any conscious sense. A naked singularity, however dramatic, is still a construct of physical law. It doesn't think, it doesn't feel, it doesn't choose, it merely exists suspended in a gravitational screen, deforming everything around it.
Unlike consciousness, which emerges from layers of complexity, interdependent networks, and feedback loops, a singularity is pure distortion. It is what happens when space and time are stripped down to their mathematical bones.
Yet the idea that such an object could interact with the universe without cognition or awareness presents a unique philosophical dilemma. In physics, observation implies a transfer of information, but what happens when the observer isn't sentient? When the thing receiving the information is not a mind, but a tear in the fabric of causality?
This is the realm of raw interaction. A naked singularity could, in theory, absorb and emit particles. It could bend light, twist space, and accelerate objects, but it would do so without filters, without purpose. It would be the universe experiencing itself without interpretation.
The closest analogy would be a camera that records, but never plays back, never edits, never understands. A mechanism that captures inputs, but assigns them no meaning. And still that kind of interaction, meaningless though it may be, matters. Because physics at its core is built on the relationships between things. Mass affects mass. Energy curves space-time. Fields fluctuate and collide.
Whether or not a singularity is conscious is irrelevant to its influence.
Its gravitational field speaks volumes. Even if it understands none of what it says, there is something unsettling about this idea that a naked singularity could bend, transform, and watch us, and yet know nothing. It's the coldest kind of attention, mechanical, blind, and absolute. It doesn't judge. It doesn't forget. It simply warps.
This concept brings to mind the ancient philosophical notion of the unmoved mover, something that affects everything while remaining untouched. But where Aristotle imagined a divine intelligence, the naked singularity is its opposite. It is not divinity, but discontinuity, not a source of order, but a rupture in it. As of now, we have not observed the naked singularity. We've only theorized. The real universe may still enforce cosmic modesty, cloaking her extremes behind event horizons. But the more we simulate and explore, the harder that assumption becomes to defend. The mathematics seems to be on the side of exposure. And if that's true, we may one day detect signs, not just of black holes, but of something deeper, something unresolved. Strange flares, unexplained gravitational lensing, time distortions with no horizon to anchor them, clues that something truly bare lies at the edge of visibility. Not all physicists agree on the interpretation of these simulations. Some argue that naked singularity solutions are mathematical curiosities, unstable under the slightest perturbation, unlikely to arise in the messy real-world collapse. A universe with dust collapsing in perfect spheres is not the one we see outside our windows. But that critique, while valid, doesn't rule out the possibility. It only underscores how delicately balanced the laws of nature might be, teetering on the edge between exposure and concealment. What if exposure is not a flaw, but a feature? What if naked singularities are nature's way of revealing that even her most forbidden truths are accessible, eventually? That behind every horizon lies the potential for revelation. If so, the naked singularity is not the villain of physics, but its muse, the ultimate challenge, calling us to rethink causality, to reconstruct our tools, to transcend the safety of cloaks and curtains.
One might even argue that the singularity is not what's naked we are, stripped of certainty, stripped of laws that always work, stripped of the comfort that there's always an equation to rely on. The moment we confront a naked singularity is the moment we confront our limits.
It's the universe in full, unapologetic clarity saying, "Here is what I am," with no veil.
Yet it remains a question whether such honesty can ever be fully witnessed. If such objects exist, they may be fleeting, unstable, ephemeral. They might dissolve back into cloaked black holes, or they may signal conditions too extreme to persist. Perhaps they require universes with different constants or geometries, or maybe we already live in such a universe and we simply haven't looked hard enough or in the right direction. Either way, the naked singularity represents a unique threshold, not of knowledge per se, but of exposure. It doesn't just sit at the end of a collapse. It sits at the beginning of a new kind of physics, one where old boundaries no longer hold, and the raw, unresolved truth of the universe stands without disguise. In that truth, there is neither consciousness nor intent. Just interaction, just distortion, just the raw, unprocessed heartbeat of space-time, pulsing through the void. Imagine an entity that never speaks, never moves in the way we understand motion, and never signals its presence through ordinary means, yet profoundly influences its environment silently and profoundly. That is a black hole. But could such an entity be likened to an observer? not in the traditional conscious sense, but through the behavior it displays in its interactions with the universe. When we peer deeply into black holes, we don't just confront cosmic silence, we confront the possibility that these dense gravitational pits might play roles that mimic observation and memory. This comparison doesn't arise from fanciful analogy, but from serious attempts in theoretical physics to understand the role of information, entropy, and fundamental limits in the behavior of black holes. The journey begins with what black holes are known to do. They encode information. Any matter or energy that crosses the event horizon, no matter how complex, simple, organic, or energetic, leaves behind a trace, not through a photograph or a logbook, but through the subtle imprint it creates on the horizon's surface. This is the starting point of one of the most counterintuitive, yet widely accepted ideas in theoretical physics, that black holes do not obliterate information, but instead store it, albeit in a manner not yet fully understood. The comparison to an observer arises here. In quantum mechanics, the role of the observer has always been enigmatic. Does a particle exist in a particular state before being observed, or is it the act of observation that solidifies its position, velocity, or spin? Now consider black holes not as active participants with eyes or thoughts, but as entities that change state depending on what falls into them. They respond, they shift. The horizon encodes. Over time, as Stephen Hawking predicted, they evaporate through Hawking radiation. That radiation, though once thought to be random, might actually carry subtle patterns, signatures of everything that ever fell inside. This possibility brings us eerily close to saying that black holes don't just store data, they act like cosmic registrars, recording without comprehension, observing without awareness. But how could a black hole possibly act like an observer if it doesn't process or interpret the information? That's the boundary where physics meets philosophy. An observer in the human sense is a conscious agent, aware, interpreting, sentient. A black hole doesn't meet those criteria. But in physics, an observer isn't always a mind. It can also mean a reference point, a node in space-time where measurements and interactions can be traced. In that sense, black holes are uniquely privileged. They mark irreversible changes. They mark boundaries. And most strikingly, they force quantum information to leave an imprint.
So, could black holes be minds? Likely not. Could they be mirrors? Very much so. Mirrors that reflect the deepest rules of the universe. They show us how entropy accumulates, how information survives, how irreversible change imprints itself on reality. In doing so, they also echo the behavior of observers, not in feeling or thought, but in function.
Part 6. Could the universe then be a mind? That remains an open question, one that treads a narrow line between metaphysics and science. But the more we study black holes, the more they seem to behave like cosmic punctuation marks, not just full stops in the stories of stars, but clauses that modify the sentence of reality itself. They are boundaries, yes, but also reflectors. They tell us where change becomes permanent, where information gets locked in, and where entropy speaks loudest. And in that role, as silent, speechless observers of the cosmos, black holes might be less like ghosts and more like lenses, not eyes that see but surfaces that encode, not minds that think but boundaries that remember. In a universe governed by information and shaped by gravity, that might be the closest thing we'll ever encounter to a mirror with a mind. What happens to time inside a black hole? How does it differ from our everyday experiences?
And could it even allow for phenomena like infinite thought during infall?
Black holes are the ultimate distorters of space-time. Time dilation, a phenomenon first predicted by Einstein's theory of relativity, becomes extreme in the presence of a black hole's immense gravity. The event horizon marks the boundary where this effect becomes especially pronounced. Time, as we understand it, flows consistently and predictably in the world we experience every day. Yet, in the realm of black holes, time becomes something malleable, twisted beyond recognition. The laws of physics, as we know them, break down at the event horizon of a black hole. As an object gets closer to the event horizon, time for that object slows down relative to an observer far away. In a very real sense, if you were to fall into a black hole, it might seem like time freezes for you as you approach the event horizon, while to an external observer you would appear to slow down and never quite reach the event horizon.
This extreme time dilation near black holes is a direct consequence of the curvature of space-time caused by their enormous gravitational pull. The closer you get to a black hole, the stronger the gravitational field becomes, warping time itself.
From an outside observer's point of view, someone falling into a black hole seems to freeze in place, suspended at the event horizon. But for the person falling in, time continues to pass normally for them, and they would experience an uninterrupted descent into the black hole's interior, except, of course, for the violent forces at play.
However, the reality of what happens inside the black hole is still largely speculative. What happens to time once you cross the event horizon, since nothing, not even light, can escape a black hole? The entire inside of the black hole is hidden from view. Time, according to general relativity, continues to flow inward toward the singularity at the center. The mind's perception of time could expand into an infinite experience, where a single moment stretches out indefinitely. This concept is more than just theoretical. It's based on the assumption that time dilation could be pushed to its extreme, where even a brief moment of perceived time could encompass what feels like an eternity from the perspective of the observer inside the black hole. From the external observer's point of view, the object falling in never quite seems to reach the singularity, frozen as it is at the event horizon. But from the perspective of the infalling object, it is a different story. Inside a black hole, time itself becomes stretched in strange ways. This stretching of time could theoretically lead to infinite experiences or perceptions for someone falling into the black hole. From a physics standpoint, the idea is rooted in the extreme time dilation that occurs as one approaches the singularity. This stretched perception could create the illusion of timelessness, where the passage of time becomes so warped that the boundaries between moments become irrelevant. It's as if the mind could be trapped in a timeless bubble, existing outside the normal flow of time as we understand it. Yet, there's a crucial caveat here. The singularity at the center of a black hole represents a point where the known laws of physics break down. We cannot describe what happens at this singularity with our current understanding of physics. And it is here that our concept of time may no longer apply in any meaningful way. In this state, one could theoretically experience an infinite stretch of thought, almost as if the mind could exist in a boundless, eternal now. But how can we interpret this? Could a person truly experience infinite thought as they fall toward the singularity? The mind's ability to experience infinite thought within a black hole is therefore more of a philosophical or speculative idea rather than something grounded in observable science. In any case,
The idea that time inside a black hole could stretch into infinity provides a fascinating backdrop for considering the nature of consciousness itself. If time were to behave so differently within a black hole, could the mind somehow take advantage of this strange bending of time to experience eternity or infinite thought?
In principle, yes, but only under certain extreme conditions that go beyond the limits of our current understanding of consciousness and the physical universe. There are those who argue that consciousness might in fact be a product of time dilation. If time could be warped to such an extent, then perhaps the mind, when exposed to such extreme conditions, might find ways to experience altered states of awareness.
Of course, this is all speculative, and we have no way of directly observing what happens inside a black hole. The physical conditions near the event horizon, as well as the nature of the singularity, present a fundamental challenge to our understanding of time and consciousness. However, the possibility of time behaving differently inside a black hole is undeniable. Whether this creates a space for infinite thought remains one of the many unanswered questions that make black holes some of the most mysterious and awe-inspiring objects in the universe. Perhaps consciousness is not limited to a straightforward progression of moments, but could be a more fluid, flexible construct that adapts to the time-distorting environments of a black hole.
Whether this results in infinite thought, a stretched perception, or a mind trapped in an eternal moment is still unknown. But in exploring the role of time inside a black hole, we are also exploring the deepest reaches of what it means to experience existence itself, caught between the relentless pull of gravity and the unknown future that awaits us as we venture deeper into black holes. In this sense, are more than just objects in space. They are gateways to entirely new ways of thinking about time, consciousness, and the very nature of reality. In the end, time inside a black hole doesn't behave like time on it. Stretches, bends, and warps in ways we can hardly imagine. As we try to peer into the darkness of black holes, we are confronted with the idea that time may not be a constant, unyielding force, but something far more malleable and fluid. The extreme effects of time dilation suggest that the fabric of space-time is not just a passive stage on which events unfold, but a dynamic participant in the events themselves.
Part 7.
Cosmos.
When we think of entropy, we typically imagine disorder or chaos, the inevitable trend toward increasing randomness in isolated systems. But could there be a deeper connection between entropy and consciousness? Could the way black holes organize entropy be similar to how our brains process information?
Surprisingly, black holes, some of the most enigmatic objects in the universe, offer surprising parallels to the cognitive processes that govern our awareness.
The event horizon to a hard drive, storing data not in silicon, but in space-time's curve.
Its state, it's not emotion, but it's transformation, input to output, governed by cosmic logic. This isn't random chaos, it's computation of a kind. Computation, after all, is information's dance. Computers shuffle bits through gates, their behavior shaped by how data flows. Black holes do something eerily similar. Their structure reflecting what they've consumed, they manage entropy, balancing order and disorder in ways that echo a system's internal logic. They don't think or learn, but they react, their horizons shifting with each encounter. This resemblance prompts a bold thought. If consciousness ties to complex information processing, could black holes harbor a flicker of awareness? Not as minds, but as patterns. This isn't to say black holes ponder the stars. They lack the plasticity of brains or the warmth of life. They're not alive, but they're not inert.
Yet their density, information packed to space-time's limit, suggests a kind of ultimate complexity.
They're sculpted by their past, active in their present, reshaping galaxies with every ripple.
In RET's terms, their integration might hint at something structural, a shadow of awareness too alien to recognize.
It posits consciousness as fundamental, like mass or charge, woven into reality's fabric.
A philosophical idea, panpsychism, pushes this further.
If true, black holes sit on this continuum not as thinkers, but as thresholds where information reaches extremes. A rock holds a trace, a brain holds a flood, and the difference is degree, not kind. Peer event horizons, encoding reality's details, might embody awareness in its rawest form, not feeling, but being, a cosmic reflection of structure itself. They don't dream, yet they respond, transforming all they touch. This view reframes black holes. They're not traps, but engines, maximizing complexity as they warp space-time. Their collisions send waves that shape nearby reality, not passively, but actively.
Physicists sometimes call black holes cosmic memory banks, not for minds, but for information stored beyond our reach.
A hint that where patterns converge, something like consciousness might stir. This isn't sentience, it's potential. Their gravity echoes the past. Every star, every particle leaves a mark. This encoding isn't readable, but it's real, altering how black holes behave. If consciousness is tied to how systems hold and process complexity, black holes offer a mirror, not alive, but resonant with order hidden in collapse. Our minds evolve layer by layer, atoms weaving patterns until reflection emerged. They show what information can do when pushed to its limits. Perhaps we're asking the wrong question. Instead of our black holes conscious, we might ask, is consciousness broader than we think?
They're not intelligent, but they're formational, hinting that awareness might be less a spark than a spectrum written into physics itself.
Black holes don't mimic brains, but they reveal a truth. Complexity breeds possibility. If it happened once, why not elsewhere? It could flicker wherever information weaves tight enough, from neurons to event horizons. Consciousness born of complexity may not be confined to flesh. Black holes don't watch the cosmos, but they reflect its deepest truths.
They remind us that meaning isn't absent in the dark, it's waiting, encoded in complexity, ready to reshape how we see ourselves, and that
the universe builds patterns, and in those patterns lies potential, not minds, but echoes. Black holes with their encoded histories stand as testaments to this idea, not as thinkers, but as possibilities.
Stars.
In the vastness of space, beyond stars and galaxies, lies a realm where reality unravels. Part 3. Here, the laws of physics tremble, equations falter, and the universe itself seems to pause.
This is the singularity, a black hole's heart.
A forbidden zone where time twists, space collapses, and comprehension fails.
More than a mystery, it's a challenge to everything we know about existence.
From dying stars to quantum frontiers, this exploration dives into the singularity's enigma, asking, is it the end of physics or the gateway to a deeper truth? Now picture a star, massive and ancient, its fires fading as its core collapses. Atoms shatter, space compresses, and the star shrinks toward a point of no return. Gravity takes over, crushing matter into oblivion. Crossing the event horizon, it becomes a black hole. Here, density surges to infinity. Space-time curves beyond measure, and the rules governing the cosmos, motion, light, time, lose all meaning. But at its core lies something stranger, a singularity. General relativity, Einstein's masterpiece, predicts this collapse. But its equations scream infinity, a signal not of victory, but of defeat.
This isn't just a cosmic quirk. The singularity is a boundary where reality breaks.
Gravity, pressure, temperature, all soar to impossible extremes, defying the tools that chart galaxies and orbits. It's as if the universe, faced with its own limits, refuses to explain itself, leaving us with a tear in the fabric of existence. General relativity, which elegantly describes planetary paths and black hole edges, thrives on smooth, predictable space-time. This failure is profound. It guides spacecraft and predicts cosmic dances. But at the singularity, it crumbles. The curvature of space-time spikes, equations yield nonsense, and physics as we know it stops. Infinity isn't an answer, it's a confession that our understanding is incomplete. A sign that the singularity hides something our theories can't yet grasp. Roger Penrose and Stephen Hawking proved this isn't a fluke. This isn't speculation, it's woven into the universe's laws. When stars die or black holes form, gravity ensures a point where space-time fails. Their theorems show that singularities are inevitable in extreme collapse. The singularity isn't just a place, it's a question, daring us to find what lies beyond. A cosmic truth that demands we rethink reality itself. If relativity falters, where do we turn? The answer lies in uniting two titans, general relativity, master of the vast, and quantum mechanics, ruler of the small.
Relativity's smooth curves clash with quantum's chaotic probabilities.
These theories don't blend easily. This clash is no mere theory.
But their fusion, quantum gravity, offers hope.
At the singularity, where scales shrink to nothingness, quantum effects might tame the infinite, revealing a reality relativity can't see. At the singularity, these worlds collide, and neither alone can solve the puzzle. Relativity sees space-time as a fluid canvas, warped by mass. Quantum mechanics insists particles behave in waves, entangled across distances, governed by chance. One path forward is loop quantum gravity, a bold idea that reimagines space-time itself. Instead of a smooth fabric, it proposes a granular structure, tiny loops, like atoms of space, woven into reality. Quantum gravity seeks a new language, one that might dissolve the singularity's chaos into something comprehensible. These loops set a limit. Matter can't compress forever. The singularity in this view isn't a point but a barrier, a cosmic no further, where physics pivots. At the Planck scale, space-time resists, halting the collapse before infinity takes hold. This changes everything. If space-time is discrete, the infinite density of a singularity vanishes, replaced by a finite quantum state. The collapse might pause, even reverse, suggesting black holes aren't tombs, but stages for transformation, where singularities mark beginnings, not ends. Loop quantum gravity doesn't just dodge infinity. It hints at a universe where chaos gives way to order. Taking this further, physicist Carlo Rovelli proposes the Planck star. From outside, the black hole seems frozen. At the Planck scale, unimaginably small, the collapse halts, forming a dense quantum core. a Planck star. When a star collapses, quantum pressure fights back, countering gravity's crush. This isn't science fiction.
Its event horizon veils what might reverse. The collapse, turning the black hole into a white hole.
A gateway spewing light and matter, perhaps to another universe. Planck's star bridges the black hole's birth and death, hinting that what seems lost might return, transformed in a cycle of cosmic renewal. String theory offers another vision, the fuzzball. It's a radical rethink of collapse, suggesting singularities are illusions masked by our limited view. Here, the singularity isn't a point, but a tangled web of vibrating strings, fundamental threads of reality. These strings, packed with quantum energy, form a complex fuzzy structure, not a featureless void. From afar, the fuzzball looks like a black hole, its event horizon smooth. But inside, it hums with activity, a chaotic dance of strings, encoding everything the black hole consumed. The singularity dissolves, replaced by a quantum knot, too intricate to call infinite. Fuzzballs challenge our assumptions. They suggest black holes aren't simple, but wildly complex, their interiors alive with possibilities. The singularity in this light is a misnomer, a region not of destruction, but a vibrant, microscopic structure holding secrets in its quantum weave. These ideas, loop quantum gravity, Planck stars, fuzzballs, reframe the singularity. It's not a cosmic dead end, but a frontier. Where physics once saw ruin, we now glimpse potential. A bounce, a rebirth, a web of strings. Black holes, far from devouring reality, might connect it, linking past to future, one universe to another. The shift echoes broader questions. The singularity isn't chaos. It's a puzzle, demanding we look deeper, beyond the limits of our current laws. The forbidden zone might not forbid understanding. It might invite it. If singularities mark transitions, not endings, what does that mean for reality's fabric?
Could they, like information or consciousness, hint at a universe more ordered than we dared imagine?
Urging us to rethink time, space, and existence itself. Yet, for all these theories, the singularity remains elusive. We can't peer inside, can't test the Planck star's pulse, or touch a fuzzball's strings. It's a boundary not just of physics, but of knowing. But boundaries aren't endings. They're challenges. A place where our tools, our math, our minds, hit a wall.
Every limit in science, from gravity's pull to light speed, has pushed us to see more, not less.
The singularity beckons because it defies. It forces us to confront infinity, to question certainty, to seek a truth beyond the chaos. We don't know yet, but the search, driven by minds like Penrose, Hawking, and Ravelli, is its own revelation. Is it a void? A portal? A mirror of reality's deepest code? Part 4.
In their mystery lies a call to explore, to imagine, to reach for a universe where even the forbidden yields meaning.
A reminder that the universe rewards those who dare to ask.
It's known as the cosmic censorship conjecture, and it suggests that nature in all her complexity has a sense of modesty.
There's an unspoken rule in the universe, one that may not be written into the laws of physics, but is whispered within the equations.
Even when she creates something as violent and unimaginable as a singularity, a region of infinite density and unfathomable force, she keeps it hidden, concealed, veiled behind the black curtain of an event horizon.
This is the realm of the naked singularity,
And it could be the universe's most shocking form of honesty.
But what if she doesn't?
What if there are moments when that curtain slips, when the veil lifts, and the singularity is exposed for all to see?
As a black hole forms, the surrounding space-time is drastically warped. This warping is described by the Schwarzschild solution for non-rotating black holes, or the Kerr solution for rotating black holes. The Kerr solution, discovered by Roy Kerr in 1963, provides a more realistic description of most black holes, as they are expected to spin due to the angular momentum of the collapsing star.
This rotation causes the black hole to bulge at its equator and introduces phenomena such as frame dragging, where space-time itself is twisted by the black hole's spin. This effect is particularly pronounced in the region outside the event horizon known as the ergosphere. In the ergosphere, objects are forced to move in the direction of the black hole's rotation, and particles can even gain energy by tapping into the rotational energy of the black hole. The Penrose process is a theoretical mechanism that allows for energy extraction from a spinning black hole. In this process, a particle entering the ergosphere splits into two fragments. One falls into the black hole with negative energy relative to a distant observer, effectively reducing the black hole's rotational energy, while the other escapes, carrying away more energy than the original particle. Although the Penrose process has not been directly observed, it illustrates the unique physics enabled by the extreme space-time curvature around black holes. Gravitational wave astronomy has revolutionized our understanding of black holes by providing direct evidence of their existence and properties. When two black holes collide and merge, they release enormous amounts of energy in the form of gravitational waves, ripples in space-time that propagate outward at the speed of light. These waves carry information about the masses and spins of the merging black holes, allowing astronomers to reconstruct the events that led to their formation. Observations from instruments like LIGO and Virgo have confirmed that stellar mass black holes, ranging from a few to tens of solar masses, are common in the universe. Supermassive black holes, millions or billions of times the mass of the Sun, reside at the centers of most galaxies, including our own Milky Way. These giants likely formed through the accumulation of smaller black holes and gas over billions of years. Their immense gravitational influence shapes the dynamics of their host galaxies, and they are often surrounded by accretion disks, rings of gas and dust, spiraling into the black hole. The friction within these disks heats the material to extreme temperatures, causing it to emit intense radiation, including X-rays. Observing this radiation has allowed astronomers to infer the presence and properties of supermassive black holes. Stellar mass black holes, on the other hand, are more elusive. They are often detected indirectly through their interactions with nearby stars or gas in binary systems. For example, a black hole can siphon material from its companion star, forming an accretion disk that emits detectable radiation. The motions of the companion star can also reveal the mass of the unseen black hole, providing further evidence of its presence. The structure of a black hole is remarkably simple, yet profound. At the center lies the singularity, a point where the curvature of space-time becomes infinite and the known laws of physics break down. Surrounding the singularity is the event horizon, the surface that defines the black hole's boundary. For rotating black holes, the ergosphere lies outside the event horizon, creating a region where the effects of frame dragging dominate. This structure is not only a testament to the power of gravity, but also a challenge to our understanding of space-time and the nature of singularities.
Black holes can also influence their surroundings in dramatic ways. When a black hole accretes matter from a nearby source,
It can emit powerful jets of particles along its rotational axis. These jets, accelerated to nearly the speed of light, extend far into space and can impact the formation of stars and galaxies. The mechanisms driving these jets are not yet fully understood, but are thought to involve magnetic fields and the intense energy of the accretion disk.
The final fate of matter falling into a black hole remains a subject of intense study. While classical physics suggests that all matter is inevitably drawn toward the singularity, quantum effects may alter this outcome. Theoretical work on Hawking radiation, which describes how black holes can slowly lose mass and energy over time, hints at the possibility of black holes eventually evaporating. However, the time scales for such processes are extraordinarily long, far exceeding the current age of the universe.
Real black holes, despite their simplicity, continue to captivate and challenge scientists. Observations from telescopes and gravitational wave detectors provide glimpses into their behavior, while black hole thermodynamics explores the boundaries of our understanding. From stellar collapse to their immense gravitational effects, black holes remain one of the most profound manifestations of the universe's underlying laws.
Quantum mechanics and thermodynamics near the event horizon. Space-time is highly curved due to the intense gravitational field of the black hole. This curvature influences the behavior of quantum fields, creating conditions where particle-antiparticle pairs are produced more frequently. The event horizon acts as a boundary that separates the black hole's interior from the rest of the universe. For one particle of the pair to escape, it must overcome the black hole's gravitational pull, which requires energy. This energy is effectively borrowed from the black hole's mass, leading to its gradual reduction. The escaping particle's trajectory depends on its position relative to the event horizon. For the pair production process to result in radiation, one particle must have a positive energy and escape to infinity, while the other, with negative energy, falls into the black hole. The negative energy contribution reduces the total mass of the black hole. This mechanism ties the emission of Hawking radiation to the fundamental properties of the black hole, including its mass, charge, and angular momentum. Black holes with no charge or spin, known as Schwarzschild black holes, emit radiation in a simple isotropic pattern. In contrast, rotating or charged black holes have more complex emission patterns due to the additional factors influencing the particle trajectories near the event horizon.
Hawking radiation also has a thermal spectrum, which means it is similar to the radiation emitted by any object with a defined temperature. The temperature of a black hole is directly related to its surface gravity and inversely proportional to its mass. This thermal nature is a direct consequence of the particle production process and reinforces the idea that black holes behave like thermodynamic systems.
The radiation emitted is incredibly faint for large black holes, making it practically impossible to detect with current instruments. However, the theoretical framework describing it is robust and supported by analogies in other areas of physics. As the black hole emits radiation and loses mass, its temperature increases. This feedback mechanism means that the radiation rate accelerates as the black hole shrinks. In the final stages of evaporation, the black hole would emit increasingly intense bursts of radiation, potentially ending in a catastrophic explosion.
For large black holes, this process takes far longer than the current age of the universe, so their evaporation is not a practical concern on cosmic timescales. However, for smaller hypothetical black holes, such as those that might have formed in the early universe, evaporation could occur over much shorter timescales, and their final bursts might be detectable.
Hawking radiation fundamentally depends on the interplay between quantum mechanics and the curved space-time described by general relativity. The particle-antiparticle pairs near the event horizon arise due to the uncertainty principle, a cornerstone of quantum mechanics. This principle states that certain pairs of properties, such as energy and time, cannot both be precisely known. As a result, energy fluctuations occur in the vacuum, creating the conditions for pair production. The curved space-time near the event horizon modifies these fluctuations, making it possible for one particle to escape and become real.
The discovery of Hawking radiation highlighted the surprising connection between quantum theory and general relativity. While these two fields describe very different aspects of nature, their intersection reveals the extraordinary properties of black holes. The ability of black holes to emit radiation also challenges the classical view of them as objects that can only absorb matter and energy. Instead, Hawking radiation shows that black holes interact with their surroundings in subtle but significant ways.
One of the remarkable features of Hawking radiation is its universality. It is not dependent on the specific properties of the black hole, such as its size or composition, but rather on the fundamental principles of physics. This universality suggests that the process is a general feature of quantum fields in curved space-time, applicable to any system with an event horizon. This has inspired research into analogous effects in other contexts, such as in laboratory experiments designed to simulate event horizons using fluids or other systems.
The study of Hawking radiation provides important insights into the life cycle of black holes. While massive black holes grow over time by consuming matter, the emission of radiation sets a limit on their ultimate longevity. As they lose mass, their properties evolve, and their interaction with their surroundings changes. In the distant future, when the universe has expanded and cooled significantly, Hawking radiation may become the dominant process affecting black holes. At that stage, even the largest black holes would begin to evaporate, although this would occur over time scales far beyond current observational capabilities.
The process of black hole evaporation is closely tied to the thermodynamic properties of black holes. The radiation emitted corresponds to a loss of energy and an increase in the entropy of the surrounding environment. This ensures that the second law of thermodynamics, which states that entropy must always increase in an isolated system, is upheld. The intricate balance between the decrease in black hole mass and the increase in universal entropy reflects the consistency of physical laws across extreme conditions.
While Hawking radiation has yet to be observed directly, its theoretical foundation is supported by extensive mathematical work and analogies in other physical systems. Scientists continue to investigate ways to detect or replicate similar processes in controlled experiments, which could provide additional evidence for this remarkable phenomenon.
The study of Hawking radiation remains an active and exciting area of research, offering new opportunities to explore the fundamental laws of nature. And that's the incredible story of Hawking radiation, a discovery that transformed black holes from silent cosmic giants into dynamic objects that interact with the universe. From quantum particles escaping the event horizon to the slow evaporation of black holes over eons, this phenomenon challenges how we understand space-time and matter.
It's a reminder that even in the darkest corners of the cosmos, there's so much left to uncover. If you enjoyed this journey into the physics of black holes, don't forget to like, share, and subscribe for more cosmic explorations. Until next time, stay curious.